Good morning everyone and welcome to the 7th lecture, which is also our second lecture on the P-block elements and their compounds. So we'll carry on in the first three videos of this lecture, going through the groups one by one. So we're going to look at group 16 in this video, then group 17 and 18. And then I'll finish off with a summary because it's been a lot to take in these last two lectures, going group by group and a lot of different chemistry. So I'll just summarise the most important points and the chemical knowledge you really need to help you predict the reactivity and periodicity, even if you forget completely what each element does itself. So now we're at group 16. We're quite far through the P block towards the right hand side, and it's here. And group 16 is called the oxygen family, or sometimes also the chalcogons, and these consist of oxygen, which is a gaseous non-metal, sulfur and selenium, which are solid non-metals, and tellurium and polonium, which are metalloid solids. The most common oxidation state is for oxygen -2, and this is one of the rules that we went through when it comes to calculating oxidation states. However, it is possible for it to be in a few different ones, like -1, and also actually +1 or +2, but we'll see that further in this video. The maximum oxidation state of the group, such as +4, +6, isn't possible for oxygen because of how electronegative it is. But +4 and +6 is possible for heavier ones, so from sulfur down. So start by looking at oxygen, and just like the other videos, we'll focus on the top two elements and their oxides and oxides and halides, because they're the most important and reactive and numerous. So oxygen, its most common allotrope is dioxygen, O2, how we all know it. And it's colourless, odourless gas, but it does have liquid and solid forms, which are pale blue. It's the second biggest component of the Earth's atmosphere, and the most important as far as we're concerned, I guess, since it's what we use to respire. And oxygen, as in dioxygen, O2, is paramagnetic. So paramagnetism isn't something we've really covered in the lectures, and I won't require you to know it for the exam, but it's an interesting concept. So basically paramagnetism is, you've got paramagnetism and its opposite, diamagnetism, and it is whether a compound has an unpaired electron or not. And this, if it has an unpaired electron, such as O2, it's paramagnetic, and that means it will interact with with a magnetic field. And then diamagnetic's the opposite. So a good example of that is nitrogen, N2. That doesn't have any unpaired electrons, so that's diamagnetic and doesn't interact with a magnetic field. So I've got a YouTube link here that shows what I mean. It's they got liquid oxygen and liquid nitrogen and pour them between two magnets, and you see how each of the liquids behaves differently in a magnetic field. So that's quite an interesting property of O2, that when it's in a liquid phase, it will actually interact with magnets. So oxygen is usually used for its oxidizing abilities. It's combustion, corrosion, respiration. These are all systems, reactions that rely on oxygen oxidizing things. It also has a second allotrope called ozone, which is O3, and this is a pale blue gas at room temperature, and you can smell it. And it's also quite important. I'll go into this more in one of the revision videos where I said I'd put some of the chemistry in a more real-world context. But ozone is a big component of the Earth's atmosphere, and you can see on this picture on the side what's called the ozone layer, or the depletion of it. And the ozone in the atmosphere is really something that keeps the heat of the sun off the Earth, and keeps it in what is a comfortable living condition for us, or a habitable living condition for us. Ozone's an even more powerful oxidizing agent than O2, so it's quite often used in things like swimming pools for killing pathogens, bacteria, things like that, and making it more hygienic. Now we can't look at oxygen oxides for obvious reasons, so we'll go straight into looking at the oxygen halides. Starting at the top of the halogen group with fluorine. So we can get two oxygen fluorides. There's a OF2 and O2F2, and these have very similar structures to water and hydrogen peroxide. So on the right here, I've got a structure showing oxygen, dioxygen difluoride. And if you replace these fluorines with hydrogen, then the structure is that of hydrogen peroxide. So very similar, it's just that the hydrogens have been replaced with fluorine. Now OF2 is a toxic yellow gas. Fluorine itself is a yellow gas, by the way. Yeah, OF2 is also a toxic yellow gas, and it's formed by reacting fluorine in the gas with aqueous hydroxide anions, so something like a basic solution, and bubbling the fluorine through it, and you'll get OF2 and also water. The OF2 can then react with the water to form hydrofluoric acid. Now, we've spoken in the hydrogen lecture, I think it was, about the hydrogen halogen compounds, and hydrofluoric acid, or HF, is at the top of the halogen group. So it's the least acidic of them, but it is very dangerous and needs to be handled with care because it can go absorb through the skin, and then the fluoride anion can wreak havoc on the body. So these are also interesting because they're the only compounds of oxygen where the oxidation state is positive. So oxygen will be in the +2 oxidation state in OF2 and +1 in the O2F2 compound. And this is because fluorine is the only element that's more electronegative than oxygen. So that's why it's the only element that oxygen will be in compounds with an positive oxidation state. We can also get these oxygen dihalides going down the halogen group, but they're polarized in the opposite direction. So in this case, when we've got OF bonds, oxygen's got the positive charge and fluorine has the negative. Then if we look at Cl2O, it's the other way around. Oxygen will have like the negative pole and chlorine will be the positive. And this is reflected in the naming as well. So it's always cation first, anion second. So with OF2, O's first because it's the cation, and then with Cl2O, also with H2O, it's because oxygen is the negative in these. And the stability of these oxygen dihalides decreases going down the group. And this is because the halogen increases in size and there's less good orbital overlap. So for example, OF2 is a toxic yellow gas. The bromide equivalent is very unstable and will decrease even before we've got to decompose, before we even get to room temperature. And then right at the bottom with I2O, that's not even possible, it's unknown. So moving on to look at sulfur now. It can be spelt two ways. I prefer with PH because British English. The F is also perfectly acceptable, it's American English. And it's got many allotropic forms. So these are rhombic, monoclinic, amorphous. They're all different crystal structures like we were looking at in the solid state lecture, the solid structures lecture. Now it's actually got the most allotropic forms of any element in the periodic table, which is quite interesting. I've also got a video up here showing a reaction of sulfur being made by oxidizing an organo-sulfur compound. It's quite interesting because it's very loud and very reactive. So I've got the link up there if you want to see a reaction that forms sulfur. So sulfur itself has no odour at all, but a lot of the compounds of sulfur, such as SO2 and H2S, really smell. They've quite often got an eggy smell. And just for a bit of entertaining science, I've got a link here. Chemistry World is actually the monthly publication of the Royal Society of Chemistry, and there's an article in there actually investigating fart composition essentially, and the sulfur compounds involved there. Now, sulfur comes a lot from volcanoes and volcanic vents, and fire and brimstone is in the Bible as the idea of hell. And brimstone is actually sulfur, and it's because it comes from volcanoes, and that's the idea of hell. So it's also found in large underground mines, and in a lot of minerals as the sulfate, which is an oxoanion. We didn't look at it in group 1 and 2, but it's similar to like the carbonates, the nitrates. An oxoanion that's very popular very common even in nature. And then 90% of sulfur produced is converted into sulfuric acid, which is apparently the #1 chemical in the US. Which surprised me, but it is used a lot as a strong acid in industry. Moving on, let's look at the oxides of sulfur. So there's two main ones, SO2 and SO3, and the structures are shown in the top right here. And they're both really important in the production of sulfuric acid. because as we said, sulfuric acid is the #1 chemical in the US. So SO3, when dissolved in water, will form sulfuric acid. I've got the reaction here. SO2, if you react it with water, doesn't make sulfuric acid. That actually makes sulfurous oxide, which is HSO3, which isn't what we want. But SO2 will react quite slowly with oxygen to make SO3, which, yeah, as we said, can be reacted with water to get sulfuric acid. So this is just, yeah, SO2 with some oxygen goes to SO3. I haven't pronounced that, sorry. But this is called the contact process, and this is quite an important industrial process, because it's used to get to sulfuric acid in the end, and this is catalyzed by vanadium pentoxide, V2O5. And this is one of the most common examples of a catalytic reaction because it's so industrially important. So let's look a bit more at this reaction, the actual SO3, once it's been made by the contact process with water to make sulfuric acid. This is super exothermic, and because it's so exothermic, the water will end up boiling and creating a mist, but this boiling water will also have sulfuric acid in it, which makes a really nasty acid mist, and is not very safe. So to do it industrially, what they do is dissolve SO3 in sulfuric acid. So obviously they've had to create this somehow first, but there's now enough sulfuric acid in the world that that's not a problem. So you dissolve SO3 in H2SO4 to make what are called polysulfuric acids. So these will be things with a formula like H2S2O7. And this is much safer, it's not so exothermic, and you don't get this corrosive mix. And then you can combine these polysulfuric acids with water, and it breaks them back down into the actual sulfuric acid that you want. And sulfuric acid is an acid, a strong acid at that, but it's also a really good dehydrating agent. So the YouTube video here that will be in the description as well is the reaction, which I've always found entertaining, of just sugar, like table sugar, with sulfuric acid, and it completely dehydrates it. So you see this white beaker of sugar turn into this massive black tower of essentially it looks like coal or something, and it is because it has turned the sugar. It's stripped all of the waters out of it, and it is just left carbon. So quite an entertaining reaction. And finally, the sulfur halides. So there are quite a few sulfur fluorides, S2F2, which actually has two isomers, where sulfur can be in different oxidation states. It can either have a similar structure to O2F2, which, if you remember, is also similar to hydrogen peroxide. Or it can also have a structure where the sulfur is double bonded to itself. And in that case, we end up with something like this. And then obviously the sulfur is actually in two different, each sulfur atom is actually in a different oxidation state to the other one, which is quite interesting. So they're all gases. SF4 is very reactive, and SF6 is really unreactive. And it's a really good electrical insulator as well. So it's used in very high voltage applications, like the actual movement of electricity from the power plant to the home in like these transformer boxes, and that SF6 is there as a very electrical insulator to keep it safer. And it's very unreactive, very inert, and very heavy. So because it's a lot heavier than air, it almost has the opposite effect to helium. If you inhale it. So helium's a lot lighter than air, so it makes you get that really high voice. If you do the same thing with SF6, you get a super low voice, and that's what this video here is, like a 40-second video from Mythbusters showing what it does to your voice. Can also make compounds with chlorine, so you can get the similar ones like S2Cl2 and SCl2, but the higher oxidation states of sulfur halide, so like with SCl6, say, like the SF6, are much less stable than the fluorides. So in the case of SF6 and SCl6, SCl6 is not actually known. And this is, like always, because of the size of the halogen as we've gone down the group.